It caught my arm walking away. And me saying the same thing. Okay, so if you've had a chance, has anybody gone on and looked at any of the videos that were up? They are up. Moving it closer was actually a great idea because now you can really see the screen. I'm pretty pleased with it. I went to the associate dean, and she said that there are instructors that film their class. Now the only downside is I can't film you guys. Okay, so the camera in the back of the class I have to shut off. Made you look. That's awesome. Yeah, I can't film you guys without your permission. So if we, for some reason, want to do a big class activity and see how it works, I'll just have you guys sign a little thing saying, yeah, it was cool to film the whole class. If you don't want to, then what I'll do is I'll put that ugly smiley face thing that they do, the computer-generated one, over your face. Okay? Then people will be like, who is that? I'll be like, Amina. Okay, so you know that you're in, right? That all the waitlisters got moved in. If not, you need to double check as quickly as possible because there are spots available in this class now. Okay? All right. So, sensory pathways, sensory information. What does soma mean again? Body. Good. Okay, most somatic sensory information is relayed to the thalamus for processing, and then some of it goes to the cortex for us to actually process properly. Now, we'll talk a little bit more about this, and we're going to have to do this when we get to other chapters, because we have to think about what's being processed and what your body will just do automatically. Visceral. What does visceral mean? Guts, fantastic. Stomach, lungs, intestine. Collected by entero. Well, that makes sense because entero, inside the body, enteroreceptors monitoring visceral tissues, organs, primarily within the thoracic and abdominal pelvic cavities. Now, these enteroceptors are not as numerous as somatic. Okay? Not as numerous, but what are they? Well, there you go. All of these seem logical except for one. Which one doesn't seem logical? Yeah, tactile does not seem logical. Nocey, pain. You eat something that doesn't work with you, you're in pain. Your heart's beating too fast because you're in love, pain. Okay? Thermoreceptors, you're overheating. Okay? Baro, well, you can't sense these, but these are the ones that are telling us we have high blood pressure or low blood pressure. And then chemoreceptors, same thing, pH, CO2. But tactile, what's up with that? Yeah. All right, so let's test it. All right? You ready for this? Are you ticklish? She's not ticklish? Can I just poke you in the stomach? She's like, sure, go for it. I was hoping she was ticklish to freak out. Can you feel this? Yeah, there's your tactile. It's not only the external surface of the skin, but if you press hard enough, you're actually going to feel it on your visceral organs. Okay? If you've ever watched a fight, an MMA fight or boxing, and you see a guy get hit in the kidneys, he's done. He's done. He's on the floor. All that pain is going into his kidneys. He's done. His body will shut down. So you've got your nocey, but then you also have your tactile. They're going to work in conjunction with each other. Alrighty? Visceral cranial nerves. Well, we already know about these, so this is nothing new. Solitary nucleus, though, a large nucleus in the medulla oblongata. Okay, major processing and sorting center for visceral. Well, go back and refresh your memory on what the medulla does. Extensive connections with the various cardiovascular and respiratory centers. And then what's reticular formation?
Awareness.
There we go. Awareness, alert, oriented. Okay, somatic nervous system as opposed to the autonomic nervous system. We'll get to the autonomic nervous system. That's our next chapter. So also called somatic motor system, controls contraction of skeletal muscle. Hey, look at that. We're going to discuss it next. Nice of them to let us know. Like, hey, guess what? That's our next slide. Woo! All right, and then chapter 16. Now, we're going to put a lot of time in the autonomic nervous system in chapter 16, but we'll get a nice little refresher with our epinephrine, parasympathetic and sympathetic nervous systems, what they innervate. Actually, it's dually innervated all the way through except for two items, okay? And then somatic pathways as opposed to sensory pathways. So sensory pathways, we have first, second, and third order neurons, right? Do we always need to go to the third order neuron? No. But that's sensory input, ascending. This is descending, which means we only have two pathways, upper and lower. That's it. Literally, that's it. So now all you need to know is where. Where are the upper and lower? It involves at least two motor neurons, upper and lower motor neurons. Upper cell body lies in the CNS, processing center. Synapses on the lower motor neuron, of course, because you're going from upper to lower. Innervates a single motor unit in a skeletal muscle. Pretty straightforward. Activity in upper motor neuron may facilitate or inhibit the lower motor neuron. Okay? Now, this is one of those ones where there's only one good explanation for it. It says activate or inhibit. Okay? So, the other day, you know, it's warming up, so I've got spiders in my house. I live out in the woods, so of course I've got spiders. And in my garage, I have wolf spiders. Okay, not hobo, because people freak out. They're like, oh my God, hobo. No, they're not hobo spiders. They're wolf spiders. They're a typical house spider. Not a big deal. The ones I have in my garage are decent sized. Okay? Okay, that's about normal. That's legs, body, and everything. That's about the size of the spiders in my garage. And they're actually more afraid of me than I am of them. So it's not a big deal. Okay, and they build tunnels, like webbing tunnels, and they come out, and yeah. So, and of course, I always have a light on in the garage, and so where do you think they congregate? Around the light, because the moths come in, flies come in the summer, and they're like, yeah, buffet. You know, it's totally awesome. Okay, so but the other day I was working on something on my bench, my workbench, down in the garage. I'm always in my garage, always. And sure enough, I looked down and he was, yeah, he's kicking it. I'm like, what are you doing? Of course, they bunch up like this when they're scared. Okay? And I just kind of brushed him off. And what would have you done? He's that big. Yeah? Can you show us what you would have done? Scream and yell, flail. Everybody has their dance, right? Does everybody have their dance? Right? Whatever you do, you freak out. Okay, so boom, that happens to you. You do your dance the first time. A week later, you feel the same thing on your arm. You feel the same thing on your arm. What's your first reaction? To do your dance. You freak out to do your dance, and you look over and you realize, oh, it's just a piece of lint. Did we inhibit our dance? Did we have to flail? We didn't have to flail. So there we go. What it's saying is, obviously things are going to happen and things aren't going to happen. If you think it's a spider, oh, phew, you didn't do your dance. You inhibited all the muscles that would normally kick in that you would flail with because of that spider. So we can actually activate multiples through upper and lower neurons, or we can actually inhibit. The uppers can say, nah, it wasn't the spider. Relax, chill. Don't worry about it. It was a limb. Okay? So the uppers can actually inhibit. They can facilitate or inhibit the lower neurons. And because we're actually going to skeletal muscle, it's a shoo-in. It's what it is. Okay? And you can actually put that analogy on anything. Anything at all. Okay? So lower motor neurons, cell body lies in the nucleus of the brain stem or the spinal cord. Brain stem or spinal cord, because we're going out now. All right? Why would we stop at the brain stem? Don't we need to innervate stuff right here? Yeah. I mean, can't all of you move your ears? Like, what? I wish I could. That'd be awesome. Right? One ear up, one ear down. That'd be so cool. But no, we're talking about moving your head and neck, shoulder muscles, postural muscles. Okay? So yeah. It says triggers a contraction in innervated muscle. Only an axon of the lower motor neuron extends outside the CNS. Only the axon does. So here's the brainstem or the spinal cord, and boom, we extend out, and here we go. We can move our arms, our legs, we can do whatever. We extend out there. Destruction or damage of the lower motor neuron eliminates voluntary and reflex control over innervated motor unit. Destruction or damage. But didn't we learn that in the PNS, if you cut a nerve, it will do what? It will repair itself. I mean, how many people have heard of people getting their fingers cut off and they sew it back on and they're like, good to go. Okay? Conscious and subconscious motor commands. Well, control skeletal muscles by traveling over 3 integrated motor pathways. Cortical spinal. Is that an input or output term? Output, yeah. From the cortex to the spinal cord. From the cortex to the spinal cord. It's motor output. The medial and lateral pathways, even though they don't actually have a directional term on them, they both do mean output. Okay? So, and the reason why they mean that is because they do actually have a word that adheres to them. So what I'd like you to do for studying purposes, write medial and write lateral, and then beside them, you need to actually do this. Rubrospinal is actually red nucleus. So we're going from the red nucleus to the spinal cord. Is that an output? Yeah. How about reticulospinal? Yeah, reticular formation to the spinal cord. Tecto? Yes. We're talking about your ability to sense different things. To touch different things. Sorry. How about vestibulo? What's vestibulo? Equilibrium. Yeah. Don't you have to control muscles to stand up straight, to move around? Yeah, they're all output because the easiest way to do this is, wow, what comes last? Spinal, 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 and spinal. If spinal's last, it's an output. If spinal's first, it is an input because we're going from the spinal cord to the brain. In this case, we're going from the brain, red nucleus, reticular formation, vestibulo, we're talking about balance, okay? This actually walks you through how they move out of the motor cortex to the different parts. Now, remember your pathways. I don't need to know where they cross over, but I do want to add this. If you see this word, please make note of it. Right here, right there. Decussation. Decussation. How about decussation? It means crossover. So make a note of it, please. Decussation actually means crossover. That was one of the very first mistakes I found in another book I was using. It said decussation, and then it actually had another word that meant crossover, so it said crossover, crossover. And I caught it, and I turned it over to the publishers, and they made the correction, because you can't actually say crossover. What does it do? Cross this way and then come back again? So they thought it was funny that I found that, but it was one of the very first mistakes I found in a textbook. So decussation just means crossover. Okay? So cortical spinal pathways, it's going to tell you what it's doing. Well, from the cortex to skeletal muscle. What is it doing? Controlling skeletal muscle. Contains 3 pairs of descending tracts, lateral, anterior. Okay? Provide conscious control. Now, this is cortical bulbar. Conscious control over skeletal muscle that move eye, jaw, face, and some muscles of the neck. So didn't I just say, if we're coming out right here, what are we going to do? Neck, head, mouth, eyes, if you're blinking at someone. Okay? Innervate motor centers of medial and lateral pathways. Cortical spinal, well, lateral tracts. Where do these come? Well, ventral surface of the medulla. What do? They cross over to the opposite side of the spinal cord. Synapse lower motor neurons in the anterior gray horn. Anterior gray horn. Anterior is also the same as ventral. We know that ventral root is what? Output. Motor output, yeah. Little cheat sheet for you. You're going to see that all these have little cheat sheets on what they do. Okay, cortical spinal pathways. I'm not too concerned about this. Remember, this is just a diagrammatic form, mapped out area of the brain. It's just saying where these areas of the brain are affected. So again, I'm not too concerned about this, but this is what they're talking about, a mapped out area of the brain. So they're saying these areas of the brain right here on the cortex control these areas of the body. All right? And interestingly enough, it's all motor, so why would we have this right here? What is that? Spine? No, it's right here. Why would we have that? Esophagus? So you can swallow. There it is. So medial and lateral pathways, just make sure that you note where they are and what their functions are. Perform at subconscious levels, okay, somatic motor command. Now, medial pathways, vestibular nuclei, superior, ooh, this is good. Let's see, who? Lucy. Superior and inferior colliculi, what do they do? Seeing, nice. Seeing and hearing what? Startle reflex. Startle reflex. So what do we do if we hear a bunch of plates crash down? Do we just sit there and go, they dropped the plates over there? No, we look over. We heard it, and we possibly saw it, but we looked that direction, so it's a reflex. Reticular formation and vestibular, you guys know what they are. Are you alert and oriented? Yes. Did everybody jump and turn their heads when I slammed the book down over there? Yes. Superior, inferior colliculi, they're startle reflexes. Inferiors, auditory. Superiors, visual. Motor output, what do? We look to that area. Vestibular, well, we're talking about balance here. Colliculi, well, superior is visual, auditory is inferior sensation. Now it says axons of the upper motor neurons in the colliculi descend into tectospinal. Tectospinal, spinal comes last, so it is a output. Good, good, good. Reticulo, well, spinal's last, so it's an output. Alert, oriented, are you aware of your surroundings? Are you aware of your surroundings? I think there's only one thing in the world that actually gets under my skin a little bit is when you're walking and someone's just not, they're oblivious. They're oblivious and they walk right into you. That's one little thing that gets oh, yeah, no touching. Those people, I don't know, maybe they're just preoccupied. Maybe they're texting and walking too. How many people have bumped into someone who's texting and walking? You should say, I never did. They bumped into me. Okay, so lateral pathways, primarily concerned with control of muscle tone. Muscle tone, axons of the upper motor neurons in the red nucleus cross to the opposite side of the brain, descend into the spinal cord in the rubro. Rubro, so rubro means red nucleus. Okay, we come down to rubrospinal, lower motor neurons of the anterior horn, brainstem, subconscious regulation of upper limb, muscle tone, and movement. So again, little cheat sheet helps you with all of the areas. And we are going to have a super quiz on this, so just be advised. It's on the weekly schedule. Basal nuclei and cerebellum, responsible for coordination and feedback control over muscle contractions, whether contractions are consciously or subconsciously directed. Okay, so yesterday I used a good example. If this floor is dry, do I need to think about it? No, I just walk. No big deal. What if the floor is icy? Do I need to think about it? Well, here's two things. Let's answer both the questions that they're talking about. Conscious and subconscious. It's icy. That is subconscious. You didn't have control over it. You didn't know it. But you went into your cat stance. You hopefully caught yourself, because if you fell, hopefully no one saw it, like your friend, laughing at you. Not even asking you to get up, but just laughing at you. The next one would be you see it's icy and you consciously do what? Hello, Louisa. You know you do this, right? Right? So, conscious control and subconscious control. If you slipped beforehand, that's subconscious. Your reflexes caught you. Hopefully you didn't fall. Conscious control, you saw it and you made the adjustments. Can you imagine if you walk like that every day? Like you're coming to class? I'll be there shortly. It's going to take some time. Right. Yeah, so we don't do that. We just walk. And if you do that, I'm going to laugh at you. I will. I'll film it. All right, so subconscious and conscious control. Basal nuclei provide background patterns of movement involved in voluntary motor activities, background patterns. Some axons extend to premotor cortex. Where's the premotor cortex found? You're all pointing to your head, but that doesn't tell me that you're like, there. Come on, Phil, it's right there. Anterior or posterior? Anterior. Anterior. Good. You're like... Weird. Okay, alters the pattern of instructions carried by cortical spinal. Other axons alter excitatory or inhibitory output of reticulospinal. So we make changes, continuously make changes. Do I need to make changes on this floor? No. Do I need to make changes when I'm going downstairs? Yeah, you do. Walking across the grass as opposed to the sidewalk? You do. So it alters continuously. It's always changing. Cerebellum, well, it monitors position, sensation, where you're at right now. It's saying, hey, are you sitting up straight? You slouching? What are you doing? All right? Visual information from the eyes. Ooh, this is good. It says vestibular balance sensations from inner ear as movements are underway. Huh. Let's test it. Let's test it, all right? Who will be my guinea pig? Who haven't I pecked on it in a long time? Susan. Oh, dear. You can stay right there, but you do have to stand up. Everybody focus up on Susan. Don't worry, I'm not going to turn the camera, so when you fall, no one will know. Okay? So, oh, you know what? She's prepared. She's got her running shoes on. Woo-hoo! Let's go jogging. Okay, Susan, front center, right here. All right, so let's test this. It says cerebellum monitors proprioception. Do you know you're standing here? Okay, she knows she's standing here. Position and sensation. She's aware of her surroundings. She's aware of what she's doing. Visual information from the eyes. Vestibular balance sensation from inner ear. Perfect. Okay, so straight up right here. You good? All right, just stay right there. Your eyes are open. You're good to go. Walk towards me. That's it. Just walk towards me. Nothing big, I know. No big deal. This is wicked cool, huh? Okay, go back and let's do it again. Okay, you ready? Okay, hold on a second. I'm going to be right here. Now close your eyes. Oh, yeah. Close your eyes. Close your eyes. Okay, and walk towards me. Now, don't even look. Watch out. Careful. What are you doing? Okay, so did we see what just happened there? Thank you very much. What happened was, okay, she knew she only had to walk a straight line. But the cerebellum says, hey, I'm going to take information from balance. I'm going to take information from vision. And I'm going to make minor adjustments for what we're doing. Very minor adjustments. Actually, none that you'll notice. Okay? So when she walked over here, her body says, okay, flat floor, this is what's going on, equilibrium's good, I'm walking. Okay? To simulate that you were standing on a dock with high waves, we'll just close your eyes. Because then what do? If your eyes are closed and you no longer have that ability to match your equilibrium up to what you're seeing, you do what? There you go. She may not have done this, which is overemphasized by me, but she did do this. Are you sure? Right? Yeah, you make adjustments. So once you lose one of those, the cerebellum says, hey, guess what? I no longer have vision. I have to go off of several other things. Things that actually don't help when I'm walking. Hearing, it's not like if I told her to be quiet, she wouldn't have heard anything. If I would have done this, she probably could have made it here. She probably would have bumped up against this. She would have followed the sound of this. But that's what it's doing. The cerebellum is saying, hey, let's monitor all of this stuff and make minor changes. When you lose one of them, it makes major changes. It says, hold on. And one of my favorites, which we can't prove in the classroom, but we can actually think about it, is this. Susan, if you closed your eyes, could you kind of remember, notice I say kind of, can you kind of remember the layout of the classroom? Yeah. She's actually taking from memory. When she closed her eyes, she immediately pulled what blueprint she had of the classroom and said, okay, I'm going to use that to the best of my knowledge and walk the line. Okay, and we do it every single day. Our bodies actually do it every single day. We have a blueprint. We have a pattern that we follow. And this is through the cerebellum. Because the cerebellum is coarse, memorized movement. You guys all walk every single day. And you come here. So now you have a pattern. And every day you come here, you have that same pattern. What if I said, okay, when you get out of your car, close your eyes and make it here? Dangerous. I'm pretty sure I'll have to actually get rid of the late thing because nobody will be here on time. Okay, walking in with black eye and bruised elbows and everything else. So levels of processing and motor control. All sensory and motor pathways involve a series of synapses, one right after the other. General pattern, spinal and cranial reflexes provide rapid, involuntary, pre-programmed responses that preserve homeostasis over short term. Okay? So general patterns. Now reflexes. Now we're all born with reflexes. They only get better as we progress in life. Now control of basic motor activities, cranial and spinal reflexes, basic motor activities. Do we have to use them a lot? No. Well, what if you're doing this? What if you're walking with a friend and you're like, and there's a little break in the sidewalk? You think you're going to use it then? Yeah, probably, because you'll probably be off step. Integrative centers of the brain perform more elaborate processing as we move from the medulla to the cerebral cortex. Motor patterns become increasingly complex. So, as we're down lower, here's a motor process, walking. Not a big deal. Okay? Now, what if I had a unicycle? First off, I couldn't ride one if I wanted to. Okay? But from here to there, how complex is that movement? Now, a bicycle, not a big deal, but a unicycle, one wheel, not going to happen. Okay? So I would have to think about it. I'd have to try to figure out my pattern. How am I going to ride that bike? Primary motor cortex, most complex. Variable motor activities are directed by primary motor cortex of the cerebral hemisphere. This is repetition from the brain. Okay? Primary motor cortex, right here, anterior frontal lobe. Levels of processing. Neurons of primary motor cortex innervate motor neurons in the brain and spinal cord. Higher centers in the brain can suppress or facilitate reflex responses. Someone tell me what that means. Can suppress or facilitate motor responses. Yeah, they can help, amplify, suppress. Yeah, they can stop different things. They can do whatever they want. And it's second by second basis. Okay? Reflexes can complement or increase the complexity of voluntary movements. Okay, so one thing that you guys need to think about, and unfortunately they don't put a good image of this, is every second of the day, every moment, every single moment, you're doing something. Your body's processing the movement saying, I need to make an adjustment here. No, I need to make an adjustment there. Okay? I know you horrible bone detachment withdrawals. Okay, they have medication for that, by the way. Just in case. So the idea is that every second you make changes. What if I say, write something on your piece of paper, and then I start moving your piece of paper? Will that change the way you're writing on it? Yeah. You'll try to compensate. You'll try to actually move with the movement. All right? You'll try and compensate. Try. All right? So, questions?